Today we're going to start off with another demonstration. So I have this tub of Vaseline and this cream lotion. So I'm going to project one of these horizontally. I'm just going to drop the other one. I want you to predict which one is going to hit the bed first. I'm going to throw this across the air in a horizontal direction. I'm just going to let this one fall. You can see that they both hit the bed at the exact same time. Feel free to try this at home and test it for yourself, but let's go and see why that's the case. Now, there's a few equations called SUVAT equations that you should remember for your exam. They may be given in your formula booklet, but I advise you to try and remember all equations, and you can do so by just simply practicing a lot of questions. Now, SUVAT stands for 5 different variables that you'll be using in calculations. S stands for the displacement, and this is in meters. U is your initial velocity in meters per second. V is your final velocity in meters per second. A is your acceleration in meters per second squared. And T is your time in seconds. Now, there are 4 main equations that you have to remember. And I'm going to give you them and you're going to have to take them for granted. But if you want to derive them and for fun, have a little bit of an exercise, if you want to try it, these equations are derived by integrating acceleration with respect to time. Okay? They're derived by integrating acceleration with respect to time. And if you put in some initial conditions like at t equals 0, the speed is u or something, you can eventually get all these equations. But I'm not going to do that here, and you won't need to know this for your exam. So I'm just going to give you them, and if you want to do this as a little exercise for fun, then go ahead. Right, so the first equation is v is equal to u plus at, meaning that the final velocity is equal to the initial velocity plus acceleration times the amount of time it took. One thing you have to know for SUVAT is that it only works for constant acceleration. But acceleration is just a constant. That could be like 10 meters per second squared, 9 newtons per 9.81 newtons per kilogram, whatever it is. Yeah, A is a constant. A cannot be something that's changing along the path or something that's dependent on time. The second equation that you need to know is S is equal to ut plus a half at squared. Third is v squared equals u squared plus 2as. And the fourth is s is equal to u plus v over 2 times by t. Now, if you're given any 3 variables, you can calculate a fourth using any one of these equations. The only situation where you'll have to use 2 equations is if you're asked to find displacement and you're given final velocity, acceleration, and time. This combination of where you're not given the initial velocity and you're asked to find one of these 4 variables given the other 3 is it almost never shows up in your paper. You can almost guarantee it won't show up. So every single equation that you need is going to be one of these 4. If you did want to know the equation anyways, the 5th one would have been S is equal to Vt minus a half At squared. But I'm saying that's an equation that you don't really need to remember and it will almost never come up. And even if you did need that, you could use a couple of the other equations to work out this answer. I would stick to remembering these 4, and you do that by just practicing a lot of questions and getting used to them. But, as I said, if you're given any 3 variables, you need to be able to know that you can pick any one of these equations and you'll be able to find the variable that the question is asking for. Now, a common type of question where you'll be able to ask to apply the SUVAT equations is something called projectile motion. An example of this is, let's say you're on a plane and your plane is dropping some food package. Let's just say, here's your plane. It's a plane. And it's dropping a food package. Okay, so that's being carried on by the plane. The plane is moving in this direction at, let's say, a speed 300 miles per hour. When this package is released, at the moment it's released, this plane is not moving vertically at any distance. Its vertical speed is 0. It's just moving horizontally. So when this package is released, it's going to be moving horizontally at 300 miles per hour. And vertically, it's at rest. So in this direction, it's 0 meters per second. Now, I want to ask, what are the forces acting on this particle? And bearing in mind, we're going to ignore air resistance in all cases, unless specified by the question. If it's moving at 0.0 miles an hour in the vertical direction, 300 miles in the horizontal, what are the forces acting on it? Well, this is not a force. This 300 miles an hour is not a force. It's just the speed at which it's moving at. The one force acting on it is its weight, mg. And we know through Newton's second law that the resultant force is equal to the mass times the acceleration. So the acceleration in the vertical direction is just mg over m, which is g, the gravitational field strength. Now when you're doing projectile motion questions or SUVAT questions, you always want to write out any known SUVAT variables for both the horizontal and vertical direction. So let's do that right now. We know horizontally, we don't know anything about distance, we're not told anything. The speed horizontally initially is 300 miles an hour. At the moment, we're not sure about what the final speed horizontally is going to be. We don't know really anything about the acceleration horizontally, and we don't know anything about the time. Now, vertically, S we're given nothing about. U we know starts off at 0. V we're not told anything about, but we could work it out. A we know is now G, and T we know nothing about. So in usually these kind of questions, they will ask you to work out S, V, or T, or something like that, or they may give you a speed being not 0 or something. Now, what the interesting thing about SUVAT and projectile motions questions is actually the horizontal motion. Now, if you look at this motion horizontally, there is no resultant force. And Newton's first law says that if there's no resultant force, object will remain moving at constant velocity. So we know horizontally, according to this equation, F is 0, so A is 0. And that means that the horizontal velocity will always be 300 miles per hour. The horizontal velocity does not change. So when it comes to horizontal motion in a projectile motion question, the only equation you need for horizontal motion is distance is equal to velocity times time. That is the only equation you need to use for horizontal motion. Vertically, they might ask you to work out speed or distance or time based on and they might give you what the distance it traveled is or the time or the final velocity it is. So the vertical motion is going to be the one that requires a lot more calculations. And the horizontal motion, the only equation you need is S equals Vt, your simple distance equals velocity times time equation. So let's look at the path of this package. We know initially it has some speed to the right, but we know that it's only accelerating downwards. So it's going to get faster downwards, whereas it's going to keep a constant horizontal velocity. So the downwards velocity is going to keep increasing. So initially it will be starting to move horizontally, but as the downwards motion velocity increases, you will see it forms this sort of parabolic path. A projectile motion follows a parabolic path because there is acceleration in only the vertical direction. So the parabolic path due to acceleration only in vertical direction. So let's look at quite a complicated example. We have a package and we're told that it's moving horizontally at 80 meters per second, because that is the standard unit for the SUVAT equations. And we're told that it's projected 80 meters per second horizontally. And the key words in these questions are if it's projected horizontally or if the question says dropped. This means that the vertical initial velocity is equal to 0. We're also told that it's going to fall in this projectile motion path and hit the surface. We're told that this height here is 200 meters. So it falls 200 meters. And we're told we want to find out what is this horizontal distance here, and I'm going to call that r. What is the range of this motion? How far horizontally does this package travel? So the first thing we always do is we write out each of our variables. We write out what is in the vertical direction, SUVAT, and horizontally we could write SUVAT as well, but we only really need to write SV and T. Let's just start off by filling it in. So we know vertically it's going to fall 200 meters, and we know that initial vertical velocity is 0. We don't know what the final vertical velocity is. We know that it's on Earth, so it's going to be falling at gravity, at the acceleration equal to gravity. We're not told anything about time, and this is what we want to find. We want to find out what is r, and we know that the velocity horizontally is 80 meters per second. And again, we don't know anything about time. The one thing about projectile motion that you need to know is that the one constant between vertical and horizontal motion is the time taken. So this time here that we're trying to find is constant for both. So we have enough variables in the vertical direction to work out the time value. We can work out time using the variable in the vertical direction, and then carry that time value from the vertical direction over into the horizontal direction to work out our range. So let's do that. So we're given S, U, A, and T, and we want to work out what T is. So we're not given V. So if you scroll up to these equations, which you should have written down, which one is the equation that has S, U, and A, and we're trying to work out T? It's equation 2, so we need to use equation 2 to work this out. So you know that S equals ut plus a half at squared. And you can almost instantly realize that, well, u is 0. So this would just be S equals 0 plus a half at squared. So for this projectile motion, when you're just projecting it horizontally, this term disappears. Now sometimes there'll be questions where it's not dropped with an initial velocity of 0. So you will have to consider this ut. In those questions, you cannot just eliminate ut like we're doing here. But because we know that the initial vertical velocity is 0, we can just cross it out because it's equal to 0. We want to know what time is, so if you rearrange this equation, you get time is equal to 2s over a, all square rooted. So you're multiplying by 2, dividing by a, and then square rooting. If you plug in some numbers, you get 2 times 200 over g. And if you plug in g as roughly 9.81, you'll get this as roughly 6.4 seconds. So we can now plug that into s equals vt. We know that s is what we're trying to find, is the r value, equals vt, which is 80 times 6.4, and that's equal to roughly 511 meters. So told in this scenario, we can easily work out our horizontal distance. Now let's go back to the very beginning where I dropped that Vaseline and I threw the other. I dropped one and I threw the other one horizontally. And I said they both hit the floor at the same time. So let's say I projected one of these just with no velocity, horizontal velocity, and the other one I projected with some horizontal velocity at the same height. So they're both at this height h. So if we do our SUVAT, and we want to find the time at which it hits the floor, so we've got, for both of them, because they're both at the same height, the height is h. We know they vertically both have an initial velocity of 0. And for, let's call this A and this one B. For B, we know that it has some horizontal velocity S, V, and T, which is what we're trying to find. And we're not told these two. But you can see from these equations that we can work out time based on the vertical motion only. So in this case, if you did S equals ut plus half at squared again, this cancels because that's 0. You would get that the time taken is equal to 2 times the height over gravity square rooted. And this is the same for both. It does not matter anything about the horizontal motion. That has no effect on the time taken for this particle to hit the bed. So they both fall and hit the bed at the exact same time. Now, in an unideal situation where there is air resistance, this will obviously not be the case. But in a situation where in your paper the air resistance is most likely going to be ignored, if you're projecting something horizontally with a speed v, or you're just dropping it so the horizontal version is 0 meters per second, they will both hit the floor at the exact same time. So in the AQA example, there is a required practical called determination of G by free fall. This may apply to the other examples, but even if it doesn't, it's quite a good practical to learn, a good skill to have to know this practical. Now, we're trying to find out G. So how do we do this? So here's the setup. You have this meter rule here, and you have 2 light gates. And you're dropping this piece of card downwards between the 2 light gates. You can use this ruler to measure the distance between the 2 light gates, and what this each light gate will give you is it measures the velocity at which this card cuts through the light gate. So it will give you the initial velocity through light gate 1 and the final velocity through light gate 2. And you can measure the distance between those two to find out the distance it travels when that velocity changes. So you can drop this card from any height. It shouldn't really matter because you're taking a U and a V reading. And we're trying to work out A, because A is equal to G. So the equation that links all of these up is your V squared equals U squared plus 2AS, where A equals G. A is what you're trying to find. You could do this experiment once. Drop the card, find a value for U, then V, and S, plug it into the equation and work out A. But the problem is that could give you quite a bad error. It might not be very precise. In your practicals, you always want to find a way to plot a graph. So how can you plot a graph from this equation? Well, you need to be able to vary one of the variables and measure the other two. So the best thing that you can vary is S, your height. You're going to be able to move these light gates up and down, and these should technically be attached to a clamp stand here. And you can move them up and down and vary the distance between them. And that will also give you different U and V readings. So we're changing S, and we're going to get different U and V readings, and we want to calculate U squared and V squared because that's what's given in our equation. It'll be very difficult to plot a graph with S against U or V because V and U are to the power of 2. So you want to plot a linear fit between them all, and the only way you can do that is by squaring the U and V values. So you're going to get a bunch of data, hopefully at least 5, and you can plot a graph. The best graph to plot in this case would be V squared minus U squared on your y-axis in meters squared per second squared against the distance S on your x-axis in meters. And your graph should be a straight line through the origin. You can see that if I moved U squared over to the other side, there is no plus C constant here. We're just going to get y equals mx. So let's plot this graph. And you may get some results that look like this. Straight line through the origin. Let's say it looks something like that. And we can now calculate this gradient. And we can see from our equation that the gradient is equal to 2a, where a is equal to g. So your value for g is just simply the gradient over 2. And that's a very simple way to determine the value of g. Now, I said in the previous video there was another Mission Impossible mistake that they made in the same helicopter scene, and let's go through that now. Now, Tom Cruise was in this helicopter above here, and he had this package below him. And there was a helicopter here. And these are both moving, and let's assume they're moving at the same speed v, because that's what it looked roughly the same on the film. Now, Tom Cruise, sitting in this plane here, wanted to drop this package so that it hit this plane. Now we know from our plane dropping package example earlier that when this package is released, it's initially going to have a velocity of v in the direction. So when that rope is cut, it's going to be moving speed v horizontally, at the same speed as both the first helicopter and the one below. Now, we know that this package is going to take a projectile motion because it's only accelerating in a downwards direction. So it's going to take a path like this. And even if you consider air resistance, without air resistance, it may take a path like that. With it, it will take a path like this. Quite similar. Now, what actually happens in the film is that what the producers thought would be the real life scenario is that as this helicopter is moving forward, they assumed that this package would drop straight down. And it almost hit this helicopter as it went past. Now, we know from our examples that that is not possible. It would have kept on a projectile motion because it is moving at speed v when it's released. So when exactly should Tom Cruise have released this package? In a real life scenario, if you were in this helicopter flying it, if you really wanted to destroy the other one, if you're both moving at speed v, the best place for you to drop this package is when this helicopter moving at speed v is actually directly beneath you. That way, by the time this moves here, it will intercept this package at this point. So it will get hit. That was a mistake in the film because what they showed is actually not possible in real life. There is no way that you could drop a package when you're in front of the helicopter at this distance here and it misses just narrowly. It would have missed by a mile. It would have missed far, far, far away. And if you were in the scenario, if you really wanted to destroy that other helicopter, you'd have to drop the package when you're right above it. And maybe you could give yourself a little small distance ahead to account for the air resistance, but not as much as what was shown in the film. I advise you to go look at some practice questions in order to help reinforce what you've learned today. It's a good way to understand how to apply the content and the equations. Please make sure to subscribe, like and comment, and feel free to watch any of my other videos if that will help you with your physics course, and good luck for your future.